Welcome to this class. It is about the field of sustainable metallurgical science and engineering. Please note that I use a robotic voice to read this class to you because this robot speaks really much better English. I work in the field of metallurgy and materials science for about 30 years. I hope to share some of my insights on the role of metallurgy on sustainability with you. This lecture is only a concise teaser. It gives a first impression of the contents of the entire lecture series, which will follow this introduction. We discuss sustainability in terms of two aspects. The first one is the sustainability of metallurgical processes, which we refer to as direct sustainability. The second one covers sustainability improvement, enabled through the use of advanced materials. We call this indirect sustainability. This is the first lecture in a series about sustainable metallurgical science and engineering. It provides an introduction to the basic aspects of this field, including such diverse aspects as economical boundary conditions, life cycle assessment and quantification of sustainability, greenhouse gases, basic definitions in sustainability, material flows and Sinkey diagrams, as well as a first view into the waste and scrap markets. Also, some first insights will be given, how sustainability will influence the next generation of metallurgical research, production, products, and markets. This presentation is a first introduction. A more detailed treatment will follow, in a number of lectures about each of these topics. What is the motivation for this class? To answer this question, we must realize the huge environmental impact of metallurgy. The global production of metals and metallurgical products stands for the gigantic number of about 8% of the total energy consumption on the planet. It is also responsible for 30% of all industrial CO2 equivalent emissions. These contribute as greenhouse gas enormously to global warming. Therefore, this class tackles the question, which solutions metallurgy can provide in that context. In the past, we have been part of the problem. In future, we will become part of the solution. Mass and energy are conserved quantities. This motivates us to develop elements for a circular economy. However, it is quite interesting to note that microstructures, which actually determine most of the properties of materials, particularly of load-bearing metallic alloys, are not conserved quantities. This simple but interesting aspect brings the question up, whether microstructures can be actually rejuvenated by adequate processing, rather than scrapping the part that is taken out of service. Alternatively, one could even think about the rejuvenation of microstructures, and the associated properties, while a part is still in service. Let me give you some examples for both direct and indirect sustainability effects. Direct sustainability effects refer to the reduction of emissions and energy consumption during the synthesis and manufacturing of metals. In that context, the reduction in the CO2 emissions, stemming from metallurgical processes, deserves highest attention. A typical example is the current attempt to inject hydrogen gas into blast furnaces. The aim is to use hydrogen as reductant, so as to reduce the fraction of iron ore reduced by carbon. A future alternative is to operate so-called direct reduction furnaces entirely with hydrogen, instead of methane gas. A second direction is the electrification of the metallurgical manufacturing chain, including, for instance, advanced electrolysis solutions. Next is the recycling of metallic scraps, and remelting them into fresh material. This requires research on advanced scrap sorting technologies, and in the future also on recycling-oriented alloy design. Recycling-friendly alloys should be characterized, for example, by a high tolerance against undesired impurity elements that can enter through the scraps. Another aspect concerns the overall process efficiency. An example is near-net shape manufacturing, such as known for instance from thin slab or thin strip casting. Next are some examples for indirect sustainability effects in metallurgy. These refer to the reduction of emissions and energy consumption that are enabled when using advanced materials for making other products, processes, or services more sustainable. A well-known example is weight reduction in the transportation sector. This is achieved by high-strength alloys, such as high-strength steels or 7000 series aluminium alloys. Of highest relevance is the increase in product longevity, achieved through improved corrosion, hydrogen, and fatigue resistance of materials and coatings. The same applies for advanced microstructure design opportunities. These can be realized through damage-tolerant and even repairable microstructures. Another important field is the improvement of the efficiency of machines that are used for energy conversion, such as turbines. This can be aided through the use of advanced high-temperature, corrosion, and creep-resistant materials. Examples are weight-reduced superalloys or iron aluminide composites. Better sustainability can be also realized when using electrical conductors with lower resistance, or magnetic materials with lower magnetic hysteresis losses, for the case of soft magnets, or higher remanence, for the case of hard magnets. These functional properties of alloys play a huge role for the electrification of industry with green energy sources. An essential contribution is made by materials that can serve for energy harvesting. Examples are thermoelectric materials, and solar cell absorbers, such as for instance, Heusler phases and perovskite solar cells. This slide shows some of the indirect sustainability effects that the use of suited materials can create in a typical production chain. The production of typical primary energy carriers, such as oil, gas, or wind energy, require high-strength alloys, with higher resistance against corrosion, hydrogen attack and fatigue. Producing electrical energy from such primary energy carriers, through gas or steam turbines with high efficiency requires high temperature and corrosion-resistant alloys. When transporting the electrical power to downstream customers, mechanically strong, lightweight, and low resistivity metallic materials are needed to minimize electrical losses. Advanced magnetic materials play a key role for enhancing the efficiency of all electrical engines and electrical transformers. When finally utilizing the electrical energy in a machine or for a specific manufacturing step, high-strength and low tribology materials are required to reduce losses that come from friction and abrasion. This schematic shows that the transmission and conversion losses, when accumulating over such manufacturing and production chains, can add up to more than 90%. This high number reveals the essential role that advanced materials can play for improving the sustainability of multiple industry operations. This simple example shows the huge opportunities that lie in the use of advanced materials that enable reducing such losses. This is a historical example which shows that recycling of metallic materials and sustainability are not new topics at all. This is a photo of a metallic lead tube from ancient Rome, produced more than 2000 years ago. It also shows the mark of the plumber who made it. Such tubes were used to bring fresh water into the many households, public baths, and lavatories. Lead was a precious material at those times. It was, therefore, frequently collected, recycled, remelted, and formed into new tubes. The fact that drinking water was transported in lead tubes might have also been a cause for lead poisoning of the inhabitants of ancient Rome. This historical case, therefore, also gives an early example of an environmental crisis. Let us now come to the contents of the lecture series. We have to start with a number of definitions in the field of sustainability. Next, I will introduce some reasons, trends, and motivation items to reveal why we have to bring our industry processes and the needs of sustainability into better accord. After that, we discuss some of the background aspects, why greenhouse gases are so important for the global warming effect. Another important part of the lecture series will deal with the underlying markets and economical driving forces behind our current ecological crisis. In that context, it must be considered that any engineering and manufacturing measure that is implemented to improve sustainability has to also obey some basic economical boundary conditions, so as to make its implementation likewise sustainable. In other words, when rendering certain steps in the metallurgical production and manufacturing value chain sustainable, somebody has to make money with this. Another important point is the influence of legislation, taxation, and social considerations. Next we will discuss how to present material and energy flows in terms of the so-called Sinkey diagrams. This is a very important tool in the field of sustainability analysis. After that, we introduce life cycle assessment methods. These are essential analysis methods in this field, for investigating the balance of all input and emission items of a product, process, or service. Another part of this lecture series will deal with waste, scraps, and recycling. Last, but not least, we will come to a number of specific metallurgical topics. In that context, we will discuss examples for current and possible future research in this field. Most of these examples come from the largest alloy groups, namely, steels, aluminium, nickel and titanium alloys. Here we start with a few basic definitions. A very general, but also very helpful definition of sustainability has been given in the Brundtland Report in 1987. It defines sustainability as a product, process, or service that meets the needs of the present generation, without compromising the ability of future generations to meet their own needs. Another, very helpful clarification in that context is that sustainability concerns the entire life cycle of a product, process, or service construction. It reaches from the acquisition of raw materials through planning, design, construction and use, to final demolition, and waste management, under consideration of all resource, emissions, and transport items. An important aspect in the field of sustainability concerns the so-called unintended consequences. This term describes the sometimes desired, but very often undesired outcomes of an originally purposeful action, that were initially not intended. This is an effect, which can sometimes be observed in cases where the side effects of certain sustainability measures have not been properly taken into account prior to implementation. Let us now look into the different roles that science and engineering play on the one hand, and society and legislative boundary conditions on the other, in sustainable metallurgical science and engineering. The tasks that we encounter in materials science and engineering are usually rather well defined, in terms of providing solutions for the reduction of the energy consumption and greenhouse gas emissions that are associated with metallurgical production and manufacturing industries, and the development of improved and new materials that enable the same effects when used in other products, processes or services. In contrast to such well-defined targets, the role of society and governmental action is much more complex, diverse, and also much harder to predict. While target quantities on the scientific side of sustainability-oriented metallurgical projects are typically very well defined, such as for instance reaching a certain CO2 reduction of a process, or a certain energy storage capacity for a battery, or a specific strength and toughness of a steel, they are much less well defined in politics, and can sometimes even change with the next election. Examples are legislative measures, changes in taxation, the development of local and global markets, the cost structures associated with products and processes, the public acceptance of certain sustainability measures, and the public opinion in general about this field, as well as cultural differences and concerns about job safety, to name but a few aspects of these permanently moving boundary conditions. The obvious consequence of such an imbalance in the boundary conditions is that they have to be considered in the form of appropriate bounds or probability considerations. These must be then included in careful model calculations, under close consideration of market mechanisms, detailed life cycle assessments, and avoidance of unintended consequences. Some of the many influencing factors affecting the field of sustainable metallurgy are shown on this slide. In this introductory session, we will not go into detail. We rather aim to get a first impression of the many influencing factors that we encounter as constraints in metallurgical projects related to sustainability. Besides the direct constraints given by the environment, and the question of limited natural resources, the focus is on economic, social, and political conditions. An important aspect is also to take into account already existing, and large-scale available technologies, and how they can be transformed to operate more sustainably. As a short take-home message from this slide, it should therefore be pointed out that metallurgical sustainability represents a true system science, with multiple soft constraints, and moving, intermediate targets. Changes to this system must be quantified using tools, such as life cycle assessment. Unintended consequences must be avoided. Also, leakage effects must be considered, so that environmental problems are not simply shifted across national borders. A further important aspect is that change management must be practiced, especially in the case of large-scale technical measures, so that engineering measures are implemented in a structured manner. Last but not least, changes in the sustainability of manufacturing-based value chains can only be realized if at least some of the parties involved make money from these changes. This overview of the sustainability goals for society and industry, defined by the United Nations, shows that the implementation of sustainability measures has multiple aspects to consider. In this lecture series we will mainly discuss aspects related to metallurgical industry, responsible production, and technologies for sustainable cities. However, the UN targets for sustainability reach much beyond that, as shown on this slide, including poverty, labor, human rights, hunger, health, and education, to name but a few other essential factors. This means that we may run in some cases into a fundamental dilemma, namely, when unintended consequences arise, that improve one of these goals, but violates another. The take-home message from this slide is that measures in metallurgical sustainability should not violate other sustainability goals. Next, we come to some definitions regarding life cycle assessment. The goal of life cycle assessment is to compare the full range of environmental effects assignable to products and services by quantifying all inputs and outputs of material flows and energy consumption, and assessing how these material flows affect the environment. This means that life cycle assessment produces a model twin of the process, service, or product considered. The model must then take all input and output quantities into account, and subject them to operational functions that mimic the targeted processes. These operational functions can be regarded analogously as the mathematical model twin of the process's digestion system. This means that life cycle assessment is a quantification tool for the total environmental impact of products, processes and services. Particularly in the field of materials processes and metallurgical products, it evaluates the environmental burdens and benefits over the life cycle for a product, from cradle to grave, including material and energy used during extraction and processing of raw materials, manufacturing, transportation, reuse, recycling, and end-of-life disposal. This requires a solid database to feed the model. This is coded in the form of a life cycle inventory. The life cycle inventory is a standardized method to quantify emissions and consumed resources, and the related environmental and health impacts, as well as resource depletion issues associated with a product's life cycle. This schematic sketch shows a typical example of a product life cycle and the workflow for its assessment. At the beginning are the natural resources and the material production. This step must consider the required energy, the feedstock materials consumed, all transportation means required as well as all the emissions created during production. Next is a typical product manufacturing step where the same input and output quantities as well as the inbound and outbound transportation are taken into account. After that comes the use of a product, which can sometimes extend over only a few hours or days such as in the case of packaging, or over several decades such as in the case of larger infrastructures and buildings. This product lifetime and all the energy input required for its operation as well as all emissions created have to be built in. The product's lifetime is an important parameter for a total life cycle assessment. The same applies to the reliable modeling of scrap availability in future scrap markets. A simple example is that materials used in buildings enter the scrap market after many decades. In contrast, a drinking can is usually scraped soon after its use. After recycling and the production of a new can, it can be back in the supermarket shelf within a couple of weeks. After that comes the product disposal where similar balance considerations must be made. An important aspect of such life cycle assessment procedures is the question, where the gates and boundaries are placed between the individual manufacturing steps along the value chain. This also determines which costs must be covered by the manufacturer and which of these costs can be externalized to be covered by society. In other words, where does a stepwise calculation start and where does it end when considering only a part of this total life cycle chain? This is important, because often these different steps along the life cycle are done by different companies. Therefore, stepwise life cycle assessments do not cover the complete through process life cycle, but only individual part of the entire chain. Such partial life cycle assessments can, therefore, provide an incorrect picture of the true environmental burden associated with a product or process. We look into this aspect in more detail on the next slide. This slide shows a schematic diagram with the different possible scales at which life cycle assessments can be conducted. On a macroscopic scale, different external system boundaries for the entire product life cycle can be defined depending on weather factors such as mining equipment, ship construction, plant construction, the manufacturing of all the plant processing equipment, maintenance tools and infrastructures, fuel industries, landfill infrastructure or recycling infrastructures are included or not. In other words, it must be decided if these parameters and the associated emissions, resource and costs are internalized or externalized. All these external borders have to be properly defined to make the boundaries of the life cycle assessment transparent to the markets and legislative decision makers. Another question are the gates between the individual steps in the life cycle. As mentioned before, it matters substantially to a life cycle assessment at which level of granulation it is conducted. For instance, when considering steel as a typical product, its primary synthesis through the blast furnace and the steel plant route comes with huge CO2 emissions. In contrast, some parts of its downstream manufacturing chain are much more sustainable due to the often very long product use and the relatively high recycling rate, for instance in the case of expensive stainless steels. This means that certain steps of a value chain and life cycle can be or can appear rather sustainable, while others appear less sustainable, and it is often an important task to make the connection among these steps transparent so that the entire life cycle is properly considered when estimating the sustainability of a certain product, process, or service. This is an example of a simple life cycle assessment of drinking cans made out of aluminium. Because secondary metallurgical production can be done over and over again, at very low environmental impact compared to the primary synthesis, thanks to the low melting point of only 660 degrees Celsius of aluminium, a used can is able to be recycled and ready for consumer use again in as little as a few weeks. Recycling aluminium cans saves up to 95% of the necessary energy consumption to create new cans through primary production. Aluminium recycling has generally a rather positive track record. More than 75% of aluminium ever produced is still in use. However, counting the total recycled fraction integrated over a larger alloy family can be sometimes misleading, also in terms of the very different time scales that different types of products are in use. It is often more adequate to measure progress in recycling in terms of the fraction of recycling that happens at the end of a product's life. In that context, the aluminium can is a nice example for a life cycle assessment. 200 billion aluminium cans are produced globally every year, which translates to 6,700 cans produced every second. For 1,000 cans, the life cycle assessment shows all the resources that have been consumed. It becomes apparent that particularly the huge consumption in electricity is a high burden. Actually, currently 2% of the world's energy use is spent on producing aluminium. This is due to the high enthalpy of formation of the aluminium oxide. Also, the consumption of water is rather high. This translates on the emissions side particularly to a very high output of CO2. This fraction can of course be substantially influenced, depending on the electricity source that is being used for electrolysis during primary synthesis. The third category lists the impact assessment, which shows how these different emissions and consumption items act on aspects, such as ozone depletion, and global warming, but also on soil acidity. Here is another example of life cycle assessment for the case of iron and steel making. With about 1.8 billion tons of iron production per year, the environmental burden associated with this material is extremely high, globally standing for about 30% of all industrial CO2 emissions. These data are taken from a publication about the life cycle assessment of steel produced in an integrated steel factory. There will be a full lecture on this topic. This slide only serves as a very concise first introduction into this complex topic. This flow diagram shows the input of coal, vapor, and electricity that is used for operating the coke oven plant, which then feeds the sintering plant, which in turn is the basis to operate blast furnaces, where the actual reduction of the iron ore takes place. This is also the production step where most of the CO2 is produced. The so-produced iron, which is also referred to as pig iron, is next transported to the steel plant. In the steel converter, the carbon is further reduced by blowing oxygen into the liquid iron carbon melt. The liquid steel, after having adjusted its desired target composition in the secondary ladle metallurgical treatment, is then cast into slabs that are further subjected to warm rolling. Casting is in integrated steel plants mostly done by using continuous casting machines, often in several parallel strands. Here we zoom in a bit, to reveal some of the details and exact numbers for the example of the converter plant. Besides the well-known input and output quantities, it is interesting to realize that also in the steel converter, substantial amounts of scrap iron are used. This scrap is required for cooling the liquid material in the converter vessel down, as the oxidation of carbon produces substantial amounts of heat. In some of the current sustainability scenarios, it is considered to enhance the cooling scrap at least by a few %, thereby reducing the amount of primary material required from the blast furnace. On the emission side, it is apparent that particularly the CO2 production in the steel plant is very high. The reason for that is that the pig iron is essentially in the eutectic point of the iron-carbon phase diagram. This means that the pig iron, coming from the blast furnace, contains still substantial amounts of carbon. This high carbon content, which is about 4.38% in the eutectic point, must be reduced prior to casting the material into slabs. This is an example for unintended consequences. The term unintended consequences refers to unplanned and often undesired side effects associated with an otherwise purposeful action. This is an effect which occurs surprisingly often in the field of sustainability. One current topic of immense importance in the field of sustainable metallurgical science is the approach to inject hydrogen into blast furnaces, in order to reduce their CO2 emission. Since about 3,500 years, iron ores are reduced by using carbon carriers as reductants. This leads to a substantial production of CO2. As a rule of thumb, Currently about 2.1 tons of CO2 are produced per 1 ton of steel. When considering the huge amount of steel globally produced, it becomes clear why about 6.5% of all CO2 emissions on the planet come from the steel industry. Therefore, the approach of using hydrogen as an alternative reduction gas is a very sensitive approach, as the resulting emission would be just plain water. Now, which kinds of unintended consequences might apply in such a scenario? First, water is a greenhouse gas too. However, water is not considered so harmful, as it contributes only a very small fraction compared to the water that is already in the atmosphere. Local saturation with water steam also leads to precipitation in the form of rain. Secondly, water splitting is extremely energy intense, and the current efficiency of this process is very low, so that huge amounts of electrical energy are required to produce green hydrogen. Third, an important precondition for the usefulness of this approach is to provide the hydrogen gas from green energy sources used for water splitting. This type of hydrogen is called green hydrogen. Green hydrogen is currently, however, not available on the market in such quantities. This means that in current industry operations using hydrogen, all the gas is essentially coming from steam reforming. In steam reforming mostly methane gas is used. The rest of the hydrogen comes mostly from the oil and gas industries. This type of hydrogen obtained from non-sustainable sources is referred to as grey hydrogen. Fourth, the catalyst materials required for green water splitting are rare and extremely expensive, and their mining also creates substantial environmental and social burdens. Fifth, if the taxation of CO2 and the prices for energy become too high, companies might simply decide to close their blast furnaces down and instead build them in other countries and import the steel slabs. This would of course reduce the local production of CO2, but not globally. Instead, the global production of CO2 would increase, due to the additionally required transportation and the use of technologies of different maturation and sustainability in different countries. This effect is called carbon leakage. It refers to the unintended consequence, that in such a case, harmful emissions are only shifted across borders. This slide gives a little case study on a materials-related sustainability challenge, namely, the design of a sustainable drinking straw. Obviously, a number of issues need to be considered in that context. These are, for instance, questions related to hygiene, sustainable material choice, the safety of the user, costs, recyclability, and so on. On the right-hand side, you can see some materials popping up, which you might want to take into consideration for solving this task. If you choose to go through this exercise, you will experience how challenging a life cycle assessment for such an allegedly simple product, its use, and its recycling can be. For instance, you may want to take the risk of harming the user very seriously, as this article in the New York Post shows. This slide provides some first facts about the different types of greenhouse gases and their effects. It shows two main categories which play a role when discussing emissions from metallurgical processes and measures to reduce them. The first one is the global warming potential over a 100 years time horizon. The second is the atmospheric lifetime of the gases. This is a property which describes how long the respective greenhouse gas remains in the atmosphere, contributing to global warming. The data show that except for methane, which is, with only 12 years, relatively short-lived in the atmosphere, all the main industrial greenhouse gases have a very long lifetime. This means that all the emissions we now produce will contribute to global warming, over at least the next 100 years, if not more. This means that the consequences of all measures that are now taken in the metallurgical industries reach far beyond our current generation. The second important aspect is that the different gases have very different influence on the global warming. The reason why the special focus in the field of sustainable metallurgy is often placed on reducing carbon dioxide and methane, is simply due to the huge quantities of these greenhouse gas emissions, compared to the other substances, which have in part a much stronger effect on global warming, but are emitted in much smaller quantities. The full lecture series will of course cover this topic in more detail. This chart gives an overview of the global greenhouse gas emissions that are associated with the main production and consumption sectors. Although this is a very busy slide, with lots of information, we learn three essential things from this diagram. The first one is that the energy, industry, transport, and household sectors are by far the most dominating ones when it comes to greenhouse gas emissions. The second take-home item is that the huge emissions that are caused by these sectors can all be substantially influenced by the types of materials that are used in these fields, and by the way how these materials are produced. In other words, the field of metallurgy has a huge leverage on the emissions for these sectors. And it must be understood that even very small improvements, for instance in creep-resistant high-temperature materials, or high-strength materials, or improved corrosion resistance of engineering alloys, can have profound positive influence on reducing energy consumption and greenhouse gas emissions in these sectors, simply due to the enormous magnitude of these sectors and the resulting high leverage effects. In other words, small progress in materials science can have a big effect on improved sustainability. The third, and rather dramatic take-home message from this diagram, is the huge reduction in greenhouse gas emissions that is required when aiming at fulfilling the targets of the United Nations Greenhouse Gas Protocol by 2050. Let us translate some of these statistics into a few key figures. They show that even small improvements in the primary production of metals can have huge impact on the total energy consumption of this sector. Metallurgy amounts to about 53 exajoule of energy consumption. This translates to 8% of the total energy that is consumed globally. The second number to memorize is that about 30% of all industrial greenhouse gas emissions come from the metallic sector. They make up 4.4 gigatons of greenhouse gas, mostly CO2. This is a slide about the embodied energy of metals. Let us take the reduction of the most important iron ore, hematite, into pure iron as an example. A standard thermodynamic database teaches us that the minimum amount of energy required for the reduction of hematite into iron is 6.1 megajoules per kilogram. This is the free energy of oxidation of iron to this oxide. This energy could, in principle, be recovered by reoxidizing the iron under controlled conditions. This means that it is the minimum thermodynamically embodied or stored energy. However, the measured energy to make iron, that is, the actually embodied energy, amounts to 18 megajoules per kilogram. This means that the production of iron from its ore has a conversion efficiency of only 33%, compared to its ideal thermodynamically embodied energy. The obvious question is, where so much energy gets lost during production? In the full lecture, that will be given in the coming lecture series about this topic, we will see that most is lost as waste heat in the blast furnace process. The conversion efficiency is even much worse for most of the other metals. This slide shows the embodied energy and the extraction efficiency for a number of metals. We learn that for aluminium and for iron, the apparent efficiency, compared to the free energy of formation of the ore, that is, the thermodynamically embodied energy, is still relatively decent, relative to the other metals that are shown in this table. The number of 23% that is shown here for the apparent efficiency of the synthesis of iron, is even smaller than the one that was given on the preceding slide for the case of hematite. This deviation is due to the fact that the number shown on this page averages over both types of ores that are used for making iron, namely, hematite and magnetite. It is indeed staggering to see how small the efficiency of metallurgical synthesis is, relative to the thermodynamically embodied energy value for most metals. This observation also reveals that there is a lot of headroom left for further research in the field of metallurgical sustainability. Here we see a comparison of the emissions that are caused by several types of materials. It does not only reveal that the metallurgical sector contributes more to the CO2 emissions than the other material classes, but it also shows the enormous increase in the emissions between 1995 and 2015. As a take-home message, it can be memorized here that the current CO2 production for making 1 ton of liquid steel is about 2.1 tons. This number holds true for the current production via the blast furnace and the conventional steel plant route. In the case that the iron ore production is done exclusively by hydrogen, and that the so produced iron sponge is thereafter melted in an electric arc furnace, leaves us with about 1.1 tons of CO2 for 1 ton of liquid steel. This can be seen as a lower bound for steel production during the next decade. Further reduction of the CO2 balance could be achieved when only green energy sources were used for operating the electric arc furnaces, and if the huge graphite electrodes that are currently used in these furnaces could be replaced by inert electrode materials. This slide shows an overview of the global annual production of the 4 biggest metal groups, as well as their specific energy consumption, the associated CO2 production, and, as an additional important category, the material that is scrapped during manufacturing. This last category is so important, because it shows how much material can be recycled in a closed-loop form, when properly collected directly during the manufacturing process. Such an inline scrap collection can contribute a lot to enhanced sustainability, because these scraps have well-defined composition and purity and can be directly remelted into new material, practically without loss of quality. Most products that are currently advertised as being made from recycled material refer to such type of closed-loop or new scraps. In this comparison, steel and aluminium stand out, simply due to the immense quantities that are globally produced every year. The most important factor that drives this enormous growth of material consumption is obviously the increase in the global population. This diagram shows an estimate by the UN Population Division, projecting more than 11 billion people on the planet by the year 2100. The scaling in material consumption, however, is not linear, because the rapidly growing global middle class leads to a much steeper increase in the demand for metal-related products. Therefore, a reasonable forecast may assume an increase in the current consumption of metallurgical products by a factor of 2, to get a robust projection for the year 2100. Such calculations are not only important to predict the future consumption of metals and products made from them, but also to predict the development of the international scrap markets, as an important source for products that can be made of recycled material. The complexity in the interplay between the world's population and the growing demands, and the resulting effects on the environment were coined through the term Anthropocene. This term describes the geological epoch, dating from the commencement of significant human impact on Earth's geology and ecosystems, including, but not limited to, anthropogenic climate and environmental changes. In other words, the Anthropocene is the geological age, where the climate and the environment are profoundly affected by humans, at an accelerating pace. Without going through these many phenomena in detail, it is just worth highlighting that many of them are very closely linked to the field of metallurgy and materials science, thereby showing that even small progress in this field can have a huge leverage on sustainability. We have to realize that we do not only encounter a revolution in sustainable manufacturing, where metallurgy has indeed a huge role to play, but we will see drastic changes in several industry-related fields that are interlinked. The first one is the coming of sustainable production, and the urgent need to improve our industrial CO2 balance. The second one is that green energy sources must replace fossil ones. If this does not happen, the first step can also not take place. The simple reason for this is that massive CO2 reductions in the metallurgical industries depend on the availability of sustainable electricity. Think of aluminium electrolysis, or of electric arc furnaces for melting iron sponge that has been made from hydrogen-based direct reduction plants. Without the vast availability of green energy, these measures do not make much sense. This refers to the next ongoing revolution, namely, electrification of transport and manufacturing processes. The last one is the digitalization and the use of artificial intelligence in modern industries. Only a complete digital twin of metallurgical manufacturing value chains allows to identify those measures where substantial leverage can be achieved in reducing the energy consumption and greenhouse gas production. It is obvious that these four revolutions are very closely interlinked. Let us next look at some of the biggest markets that drive the metallurgical production. Here we first look at the global market for light vehicles. The diagram shows the high growth rates in this field, and it also reveals the fact that we currently sell an incredible number of about 100 million cars every year. This translates roughly to a total value of 2,000 billion euros per year. In total, we have about 1.3 billion cars on our streets already today, with 50 million units alone in Germany. We all know that it would be much more responsible and ecologically compliant if we would either ride our bicycle or use such eco-vehicles, like the one shown here, made of scrap and renewable materials. Reality, however, is a bit different. The customer is king, and as a king, the customer prefers to rather ride cars like this subtle vehicle shown here. This is just to demonstrate the simple fact that there is often a big discrepancy between the desirable behavior of entire industrialized societies on the one hand, and the individual behavior of customers on the other hand. Sometimes, this discrepancy is interpreted as a conflict between the consumer behavior of the young generation versus the consumer behavior of the older generation. However, this view is not quite correct. This becomes clear when you take a quick look at the ecological fingerprint of the global Internet. The use of the Internet and its many associated services has meanwhile reached similar energy and CO2 emission numbers as the total global air traffic. This somewhat busy table shows that most of the Internet traffic does actually not serve to produce manufacturing value for society, but most of it is instead used for unproductive or even dull entertainment. This simple comparison between the Internet and the global air traffic shows that the environmental challenges and the market forces that drive our current consumption of energy and the production of greenhouse gases does not simply result from the behavioral patterns of certain parts of the population, but it reflects a global trend of all industrialized societies as a whole. The global market for smartphones is a similar example. This diagram shows the immense growth in the number of smartphones that are sold each year. In 2019 we reached the incredible number of 3 billion smartphones shipped to end customers per year. One of the main questions in sustainable metallurgy is, what happens with these phones if we do not use them anymore? These phones produce obviously a correspondingly huge pile of electronic scrap every year. This diagram gives a rough impression of the gigantic quantities of electronic waste generated per year. It shows the interesting detail that countries such as China and the United States are among the biggest producers of electronic waste. However, when counted per person, other countries such as Germany and France produce much higher quantities of electronic waste. The next slide shows the interesting fact that modern smartphones can contain nearly half of all known elements in one little gadget. It also reveals that for some of the most expensive ones, for instance, for the rare earth ones, such as lanthanum, yttrium or terbium, the recycling rates are below 1%. Here we see the enormous increase in the global steel market. Today we see the gigantic amount of more than 1,800 million tons of steel consumed every year, and the further trend points upwards. This huge consumption of steel is due to its vast availability, its very low price, and its excellent mechanical performance when serving in numerous load-bearing and also many functional applications. While large quantities of steel are used in the automotive, manufacturing, and mechanical engineering industries, by far the highest fraction, of more than 50%, goes into huge construction and infrastructure applications. Very similar trends apply also to aluminium and the other metallic materials, such as nickel or titanium alloys. The total global market for metals amounts to the incredible number of 3,000 billion euros per year. On the next slides we look into some Sankey diagrams for 4 important metallic materials. A Sankey diagram is a type of flow figure, in which the width of the arrows and connection lines is proportional to the flow rate of quantities such as material or energy. The following illustrations show Sankey diagrams that represent all the material flows associated with the production, use and waste of steel, aluminium, nickel, and titanium. The first example shows the flows for steel, from the mined ores, to the final stock and scrap. It reveals not only the huge amounts of ores that are consumed for steel making, but it also shows the secondary synthesis where new steels are melted from scraps in electric arc furnaces and fed back into the market. The user bar also shows that more than half of all steels go into construction. The next Sankey diagram is for aluminium. It reveals that currently less than a third of all used aluminium is made from scraps. This means that there is substantial room for further improvement, since secondary production of aluminium from scrap uses only about 5% of the energy required for synthesizing primary aluminium from ores. Another interesting detail is that the use of aluminium is quite evenly distributed over different sectors, ranging from packaging to construction and transport. The latter market is currently substantially growing, owing to the increased use of aluminium in vehicles, for weight reduction purposes. For the case of nickel, the Sankey diagram shows a high fraction of scrap produced during refining. It also reveals a high contribution from old scrap, coming from end-of-life products, which can be injected back into fabrication. Most of the nickel is used in stainless steels, as reflected by the product portfolio where it is mostly used, namely, in household appliances and industrial machinery. Nickel-containing products, such as stainless steels, are very durable, and serve in parts and equipment that are designed for long-term use. This means that nickel-containing products have a certain inherent sustainability, due to their longevity, as the best scrap is the scrap that is avoided. Titanium is the most extreme case, when it comes to losses during manufacturing. The Sankey diagram shows that huge amounts are scrapped in the mills and from the titanium ingots. This means that the prevalent resource for recycling titanium is in-house scrap, produced in smelting and fabrication, instead of post-consumer titanium products. Consequently, the current recycling rate including cascade recycling in smelting and fabrication is high, motivated also by the high price of this material. The vast majority of parts made of titanium is used in aircraft components. One basic question is whether we have too many different types of alloys, with too many different chemical compositions. We are nowadays regularly using more than 2,000 different types of metallic alloys, many of which have quite different composition. This makes scrap sorting of course much more challenging, particularly when considering post-consumer scrap, where everything is mixed together. This leads to substantial downgrading in material quality and downstream recyclability. In contrast to the approach of designing and adjusting alloys and properties primarily through their chemical composition, the possibly biggest success story of modern metallurgy is the understanding that many properties, particularly the mechanical properties, can be instead very well realized through the adjustment and tuning of the microstructure. This also points back to our initial statement, namely, that the microstructure is not a conserved quantity, and can be substantially influenced by processing, in a way to alter for instance the mechanical properties over several orders of magnitude. The most famous and probably most successful material in that context is steel. Based on a small range of very simple chemical compositions, including for instance iron, carbon, and manganese, a surprisingly huge variety of microstructures and properties can be realized, serving in more than several hundred quite different types of steels. As an example, a bulk iron single crystal can be as soft as 30 to 40 megapascals, while heavily wire-drawn pearlitic steel can be as strong as 7 gigapascals. Interestingly, a similar variation of properties applies also for many natural materials, such as for instance wood, which yields a huge variety in mechanical response with essentially using the same chemical ingredients and building units, realized mainly through the adjustment of its hierarchical structural organization. This diagram gives a nice overview about the number of chemical elements used in materials and products over time. While in the past centuries, only few elements, such as iron, copper, carbon and lead were used, modern machines and electronic devices use in part materials with more than a third of all known chemical elements from the periodic system. This means that we encounter today a massive chemical mixture, when these parts return in the form of scrap. This poses an immense burden for the recycling industry, because mass is a conserved quantity, and many of these elements are very rare, and in part extremely expensive. Yet, due to this enormous variety of elements used in the same material and product, it is increasingly difficult, or even impossible, to separate them from each other, when the product has reached the end of its life. This intense mixing of elements is also due to the fact that we can nowadays design, manipulate, and manufacture materials at dimensions that reach down to the nanoscale. A similar view applies for metallurgical products. The past few years have seen an immense increase in the chemical variety and magnitude of the alloying content of advanced alloys. This is a trend which makes recycling extremely challenging. Hence, a sensible alternative future trend might be to achieve property optimization not through chemical variation, but instead through microstructure variation. This is an overview of the tensile strength values for a broad variety of different commercial wrought aluminium alloys. The aluminium alloy family falls somehow between the iron-carbon steels, where a huge variation of properties can be achieved with practically the same composition, and the more complex high-entropy alloys, where most of the property variation comes through adjustment of the chemical composition. The alloys belonging to the 1000 series group, on the left-hand side, are relatively pure aluminium, such as for instance used in packaging. The 3000 series alloys, blended with manganese, are used for instance in beverage cans. Next in that sequence are the higher strength alloys, pertaining to the 5000 and 6000 series. Alloys of the 5000 series are essentially blended with magnesium, while those of the 6000 series use both magnesium and silicon as alloy ingredients. These two types of alloys are primarily used in the automotive sector, as well as in mobile phones and laptops. The high-strength alloys of the 2000 series use copper as primary alloying element. These materials serve mostly in the aerospace industry. Even higher strength levels can be achieved when doping aluminium with copper, zinc, and magnesium. Alloys of this type are gaining momentum in the automotive sector. This means that, from left to right, most of the strength increase is obtained by adjusting the chemical composition, together with the corresponding heat treatment that is required, to achieve the desired nanoprecipitation state. What is interesting in this diagram, is that for some of the high-strength materials, a broad variety in tensile strength can be obtained by different heat treatments alone. These lead to different nanoprecipitation states in alloys that have essentially the same, or very similar, chemical composition. Urban mining refers to the process of reclaiming compounds and elements from products, buildings, and waste that would have to be otherwise mined and enriched by traditional mining methods, a field that is often associated with a substantial environmental burden. Let us look at the example of rare earth elements. These metals are important in producing multiple goods that people want, for instance in the form of magnets, electronics, batteries, solar panels, or lasers. However, mining these rare earth metals from the earth can, ironically, be very detrimental to the environment. As the push for green technology accelerates, the challenge of obtaining rare earth metals without becoming an environmental problem itself, will therefore require creative solutions. Urban mining is one of them. Today many precious metals are still ending up as landfill and only small fractions are retrieved from mixed post-consumer scrap. Since mass is a conserved quantity, however, it is urgently required to find ways to avoid creating so much scrap in the first place, and identify environmentally friendly methods of reclaiming metallic elements from urban scraps. The most rapidly growing source for urban mining of rare and expensive elements is the electronic and electrical waste. It stems from computers, television sets, mobile phones, and household appliances, which implies that it mostly occurs as post-consumer scrap. This means that it is mixed with other types of waste. Most of this highly precious material is ending up as landfill. When such electrical and electronic waste can be separated from other waste streams, it represents a very valuable source for urban mining. As an example, mining gold from classical ore deposits yields about 5 grams of gold per ton of ore. The value is very similar for the platinum group metals, which are essential for instance for green chemistry, as most catalysts are made of these elements. In contrast, the yield in urban mining can be up to 300 grams of gold per ton of electronic scrap, for instance, when retrieved from old cell phones. The numbers are equally high, or even higher, for different types of electronic products. Particularly in the electrification of industry and transportation, as well as in green energy harvesting, substantial unintended consequences can apply, when obtaining the materials and elements that are needed in this field. To be specific, more than 3 billion tons of minerals and metals are required to deploy wind, solar and geothermal power to an extent that enables us to keep the global warming below 2 degrees centigrade. This means that while sunshine and wind are clean, the infrastructure that is urgently needed to capture it is not. The huge increase in extraction of metals and minerals needed for tapping green energy sources comes at a very high ecological and social burden, which must be properly understood and mitigated by implementing adequate engineering solutions. This diagram shows for some of the minerals that are urgently needed for making our energy supply and infrastructures more sustainable, the projected growth rates until the year 2050. It shows that the demand for some of these materials will grow by the incredible amount of 500%. This means that sustainable approaches must be identified, for the mining and the synthesis of these materials, but also for more closed-loop recycling and retrieval of material from urban mining. This diagram shows differences among recycling rates for different material and product groups. The recycling rates for steels are rather high. This applies traditionally for steel from scrap cars, and for stainless steels, coming from household appliances. For aluminium, the recycling rates are quite different for different product types. While 2/3 of all beverage aluminium cans are recycled, the total recycling rate, averaged over all aluminium products, is only about 40%. The lowest recycling rates are observed for polymer bottles. This diagram teaches us that we have to develop recycling rates in closed loops, pertaining to specific product and alloy groups, with early-stage separation of different types of alloys. The most efficient type of recycling is the collection of specific alloys directly during manufacturing. This will be discussed in greater detail in the following classes. We will then also discuss the requirement that future products must be upfront developed in a way to allow for efficient disassembly and separation of the different materials. This figure shows that in spite of the fact that several materials contained in end-of-life products have recycling rates above 40 or 50%, recycling's contribution to overall demand for these materials is generally very low. The gap between these two essential parameters is particularly large for some of the major metal groups, such as iron, aluminium, and nickel, but also for some of the precious metals, such as the platinum group elements. This shows that high efficiency of the recycling industries in the European Union in recovering materials from end-of-life products alone does not always correspond to a proportional contribution in terms of increased resource security. This means we need to also develop sustainable methods of mining and primary synthesis of new material. It should also be highlighted that many raw materials are contained in long-use societal stocks, entering the recycling loop only after a long period, sometimes decades. An interesting question is what the driving forces are for developing sustainable products, processes, or services. Recently, it is for instance the consumer who gets more sensitive about the sustainability of products, although the price still plays the leading role for customer decisions. This applies particularly for customers with low or average income, who can often not afford paying a higher price for more sustainable products. This is a challenge, where often state legislation and taxation measures can come into play, for instance through lower taxes, or financial benefits, to encourage customer decisions for sustainable products. In some cases, companies anticipate legislative decisions, and develop more sustainable products of their own, such as for instance in the case of banning lead-containing products from solder wires. Another main factor for pushing governments to take measures for rendering industry and products more sustainable are international treaties, such as the Kyoto or the Paris Protocols. A classical example where green branding works, due to the high recycling rates, are aluminium cans. After scrapping and collecting them, they can be back in the supermarket already after several weeks. The energy that is saved by using scrap aluminium, instead of primary aluminium, is about as high as the energy of the gasoline that would fill the can. A more long-term and more general challenge is to develop a broad range of products and processes that can benefit from green branding, even if the product price exceeds that of a less sustainable competing product. As an example, in the food industry, this has been achieved to some extent. The organic food and beverage market is expected to reach a volume of about €330 billion by the year 2022, with an annual growth rate of about 16%. The images show some examples of products which use green branding. In all such cases, it must be of course carefully checked and controlled, for instance by using life cycle analysis, whether the green branding is justified or not. Products sold under this notion, without being truly sustainable, are referred to as greenwashed products. The classes that come later in this lecture series will provide you with the tools and understanding to conduct such analysis and design products that are truly sustainable. In some cases, metallurgical societies and industry consortia are starting to define joint guidelines for sustainable processes and products, so that these terms become better protected, and cannot be used in an arbitrary way. However, it is in many cases recommendable to double-check these guidelines, and subject them to a life cycle analysis. A famous quote says, that you cannot cross the sea by standing and staring at the water. Applied to this lecture series, this means that we have learned much about the metallurgical sustainability problems, but we must also take steps to develop concrete metallurgical projects to improve the situation. Let us take a quick look at aluminium. There will be a full class about it in this lecture series, so that I show here only some of the essentials. Aluminium is one of the fastest growing markets in the field of structural alloys. It serves in many applications, where low weight and high strength are required. Aluminium is very corrosion resistant, due to the thin and dense oxide layer formed on its surface. Its melting point is very low, only 660 degrees centigrade. This means that melting aluminium scraps into new material comes at very low energy costs, only 5% of what is used for its primary synthesis. However, aluminium alloys are also very composition sensitive, and retrieve their good mechanical properties from a complex set of nanoprecipitates. Therefore, aluminium alloys should not be mixed, but require very good scrap separation prior to recycling. The most important feature of aluminium alloys, regarding sustainability, is the high difference between the energy consumed for primary and secondary synthesis. The term secondary synthesis refers here to the remelting of aluminium from scraps. While primary synthesis, through electrolysis, costs 45 kWh per kilogram of metal produced, the melting of scrap into new material costs only 2.8 kWh per kilogram. Another factor, making a huge difference in the material's sustainability, is whether the electrical energy for the primary synthesis comes from sustainable sources, or from fossil fuels. Since aluminium alloys are highly sensitive to composition changes, aluminium scrap sorting is one of the most essential tasks in secondary synthesis. Mixing different aluminium alloys can lead to the formation of large and blocky intermetallic particles that form during solidification, and make the material brittle and susceptible to failure. Another important aspect in the context of secondary synthesis is the limited availability of certain high-quality scraps on the one hand, and some less desired scrap types in the recycling loop, such as certain cast alloys, on the other hand. This comparison analyzes the carbon footprint of an aluminium drinking can. The color bar gives the carbon footprint in grams of CO2, embodied in a 330 ml sized can. The range between minimum and maximum depends on the specific origin of the fossil fuels that were used during production. An aluminium can that uses less than 50% of recycled material, and correspondingly more than 50% of primary aluminium, produced by using fossil fuels for electrolysis, has indeed a very high carbon footprint. The smallest carbon footprint applies when a high content of recycled material is used, with only minimum input of primary aluminium, and when most of the cans are recycled into new ones. Also, the use of renewable energies strongly reduces the carbon footprint of such a product. The main take-home message of this slide is that not certain products are sustainable or non-sustainable, but the product's sustainability depends to a great deal on the origin of the energy, and the raw materials that are used to manufacture it, and its end-of-use recycling rate. This is a rough overview of the many different types of aluminium alloys, and their compositional ranges. Details related to the sustainability and recycling of these alloy classes will be the subject of an individual lecture. Here I only give 3 snapshots of quite different scenarios. A high silicon content of up to 14 weight % is commonly used for cast products, since the silicon compensates the thermal shrinkage of the aluminium and enhances castability. Huge quantities of such alloys serve in automotive engine blocks. However, with the transition of mobility from gasoline to electrical engines, they are no longer used, and new products or alloys must be invented to consume such sort of scrap, which will enter the market during the next 15 years. It must be emphasized that such a high silicon content cannot be tolerated in any of the existing wrought alloys. A similar situation applies for the 2000 series alloys with high copper content. This element lends the material very high strength, but it is undesired in most other aluminium alloys. Iron is another element that enters through the scrap and through the recycling of cast alloys, but it is undesired in most wrought alloys, such as the 5000 and 6000 series materials, as it promotes formation of brittle intermetallics. Aluminium alloys with high copper content are the most widely used heat-treatable alloys for aircraft materials, mainly due to their high strength-to-weight ratio. However, the copper-rich precipitations, particularly aluminium-2-copper intermetallics, and their spinodal precursors, which strengthen these materials, have negative effects on their corrosion properties. Hence, scrap entering the market from aerospace products is typically undesired when making new aluminium alloys. An interesting concept is to let the liquid aluminium not cool down before shipping it to customers, where it has to be melted again for continuous casting, but instead bring the liquid material directly to the customer. This does not only save the energy required for reheating, but the liquid metal serves also as a buffer medium for storing energy. The operation of the electrolysis, for reducing the metal, can be done in a flexible way, buying traded electrical power when it is inexpensive, such as at nights and weekends. In such a business concept, where liquid metal is transported on public highways, safety is of course an important issue. This graph shows the global demand of aluminium, highlighted in terms of two categories, namely, aluminium made from primary production, and remelting of scrap aluminium. The data show that only about a third of the aluminium is recycled from scrap. Therefore, research in this field aims at increasing the total recycling rate of aluminium. This requires to not only think in established alloy classes, but also about new alloy concepts that combine different aluminium classes and their respective alloying elements. Such materials that combine established types of aluminium alloys with the aim to make them more tolerant against tramp elements intruding from scraps are referred to as crossover alloys or uni-alloys. This is a little exercise about the difference between indirect and direct effects on sustainability. The example is a body-in-white structure for a sport utility vehicle, with a mass of more than 1,700 kilograms, containing about 9% of aluminium in the original design. Let us start with indirect effects that improve the sustainability of this vehicle. A weight reduction of nearly 30%, translating to 474 kilograms, can be achieved when increasing the aluminium content up to 37 weight%. This leads to a linear reduction of the fuel consumption. With that, lightweight structural materials, such as high-strength aluminium alloys or high-strength steels, contribute substantially to more fuel-efficient vehicles. A second step can be taken by improving also the construction's direct sustainability. This means that for all the materials that are used for the body-in-white, more sustainable production and manufacturing can be used. For the case of aluminium, an amount of 35% CO2 and energy reduction can be achieved when using recycled aluminium made from scrap, instead of aluminium alloys made from conventional primary production. Let us look closer at the recycling of aluminium alloys. These materials can usually not be mixed among the different grades, but must be carefully sorted prior to remelting. This is due to the fact that current aluminium alloys are highly optimized for strength, ductility, surface appearance, corrosion, toughness and formability, to name but a few key features. When blending undesired tramp elements into such established alloy grades, some of these properties can substantially worsen, for example, through the change of the precipitation kinetics, segregation, the formation of undesired and large intermetallic phases, or changes in the precipitation-free zones that surround the decorated grain boundaries. The best way to get clean scrap is closed-loop recycling, where the scrap is directly collected during production and manufacturing. In such cases the scrap collected is well defined and can be directly melted again. A large fraction of the aluminium scrap, however, is post-consumer scrap, which is mixed. In such cases, X-ray and plasma-assisted chemical online analysis methods can be used to classify alloys with respect to their prevalent alloying elements, such as for instance manganese, copper, iron, or zinc. As the results, obtained from the online chemical analysis, are in the form of complex spectra, advanced machine learning techniques are increasingly used for the identification of the alloy encountered. Combining this online analysis with fast computer monitoring, optical particle detection and tracking, and a mechanical sorting system, allows to assign and sort scrap particles to specific aluminium alloy classes. Details of these recent advanced recycling and sorting techniques will be the subject of a full class in this lecture series. This movie gives an example from a research project on impurity-tolerant aluminium alloys. It shows data from a tomographic atom probe measurement, conducted on a 3000 series manganese-containing aluminium alloy, used for drinking cans. Atom probe tomography is a method that allows to measure the chemical composition of complex materials at the near atomic scale. It works by combining ionization and field evaporation of atoms from tip-shaped sample surfaces under high electrical fields, combined with a mass-to-charge flight spectrometry and a position-sensitive multi-channel plate detector. The data show that besides the nominal alloying elements, such as about 1% manganese, 1% magnesium and a bit more than 0.1% copper, a number of further elements accumulate over the multiple recycling and remelting cycles it has been going through. It is therefore an important question in current research to understand how many and how much of these tramp elements can be tolerated in recycled aluminium alloys. A further question is, whether alloys can be developed, that are upfront designed for high impurity tolerance and hence, for high scrap usage. Next we look into a few sustainability topics related to steels. With 1.85 billion tons produced per year, it is the most important material class in terms of volume and environmental impact. While steel is a sustainability enabler, for instance through lightweight design, magnetic devices, and efficient turbines, its primary production is not. Iron is reduced from its ore using carbon. Today 2.1 tons CO2 are produced per ton of steel, causing 30% of the global CO2 emissions in the manufacturing sector, which translates to 6.5% of all CO2 emissions on the planet. This qualifies steels as the material group with the highest leverage for improvements in sustainability. Again, a full class about this topic will follow, and I give here only a few first glimpses. Let us first take a look at the blast furnace and its impact on CO2 emissions. It is interesting to note that the carbon that finally produces the CO2 is not contained in the ore, but it is added to serve as a reductant. Its second role is to reduce the melting point of the iron in the blast furnace. Pure iron has a high melting point of about 1536 degrees centigrade. The so-called pig iron, that is tapped from the blast furnace, is not pure iron, but a eutectic iron, 4.38% carbon alloy, which has a much lower melting point of only 1147 degrees centigrade. The problem is that this very high carbon content must later in the steel converter be removed again, producing lots of CO2. This shows that the cause for the staggering production of CO2 from conventional iron and steel making is the use of carbon as a reductant. One approach to mitigate greenhouse gas emissions from the blast furnace and converter lies in injecting hydrogen into the blast furnace. Currently, about 300 kilograms coke and 200 kilograms pulverized coal produce 1 ton of pig iron. The reaction product is CO2. When using instead hydrogen, water vapor is the reaction product. However, in a blast furnace, coke is generally required, to lend the furnace its permeable inner structure, allowing gas percolation, as well as slag and metal tapping. Therefore, in a blast furnace, only a fraction of the ore reduction can be achieved by hydrogen. Current pilot plants use also coke gas for this, as it can contain up to 65% hydrogen and more than 20% methane. Details of the interplay among carbon monoxide and hydrogen in the reduction reaction are currently under investigation, and will be discussed in a separate class. A second method to reduce CO2 in iron making is the direct reduction method. In this approach, solid iron ore pellets are exposed to a reducing gas, usually methane, which reduces iron oxides to metallic iron at temperatures below the melting point of iron. The so reduced material is called sponge iron. It can be molten in electric arc furnaces, instead of converters, because the sponge iron from direct reduction contains only negligible amounts of carbon. The direct reduction process is comparatively energy efficient. Like in the blast furnace, hydrogen can be used as reductant, instead of a carbon carrier gas. The big advantage over the blast furnace is that even pure hydrogen can be used. For these reasons, hydrogen-based direct reduction furnaces are considered the next generation technology in clean iron making. A precondition for this is of course, that green hydrogen is used for the reduction. This figure shows the impact and technology readiness of sustainability measures for structural alloys. The assessment is grouped along two axes, the scaled potential for impact versus technology readiness. Colors correspond to metals where the opportunities are most significant, and where there is no color, opportunities across all metals will provide value. This analysis helps to assess the effects that the different measures can have on enhancing the sustainability of structural alloys. The highest impact and at the same time highest technology readiness applies for corrosion protection. When considering that more than 3% of the gross domestic product of industrialized countries is annually destroyed by corrosion, the huge leverage of corrosion protection on longevity and sustainability becomes clear. A similar effect can be reached through the electrification of the metallurgical industry, provided that the electrical power is supplied by renewable sources. A huge impact can also be attained when generally reducing scrap production during manufacturing, and the closed-loop collection and sorting of such scraps already during production. This also avoids that high-quality scraps of well-defined chemical composition are mixed and hence lose value. There are several other techniques with high technology readiness, and they will be discussed in the following classes. Interesting opportunities for research and more long-term development lie in the CO2-reduced production, such as discussed for the case of iron, the recycling of material within larger alloy family groups, and the upfront recycling-oriented design of new alloys which are more tolerant against impurities intruding from mixed scraps. Further opportunities lie in the reuse of alloys and in the higher damage tolerance of materials. Alloys with very complex chemical compositions, however, are more attractive for niche applications, with small leverage on the reduction of greenhouse gases. However, they may have potential in energy-critical applications, where for instance high resistance against hydrogen embrittlement is required. This slide lists a number of further direct sustainability measures, ranging from advanced electrolysis methods to smarter ways how we collect, use and avoid scraps. You can take this small compilation to think about further ideas yourself. You will be surprised how many ideas emerge that can improve the direct sustainability of metals. The same applies for the indirect effects, where sustainability progress is achieved through the use of advanced materials. This list only shows a few examples, some of which are well known from textbooks, such as strong and lightweight metallic materials, while other ideas have been less studied, such as alloys that are specifically designed to reach their desired microstructures with short and low temperature heat treatments. The more you think about such opportunities, the more interesting materials problems you will find, that might help to improve the sustainability of materials. So, we have reached the end of this introductory class about sustainable metallurgical science and engineering. I hope you enjoyed it. A full lecture series about this topic will follow, where we have the chance to go into much greater detail of this emerging and exciting new field. Thank you very much for attending and see you soon again.